progress of big data machine learning in hydrology and groundwater resources, where do we go from here? Well, I'm hoping for some answers to that question from Dr. Chaopeng Shen, who is currently an associate professor in civil engineering at the Pennsylvania State University and an associate editor of the Water Resources Research. Thank you for taking the time for being here.
Thank you very much. Thanks for having me here. It's a huge pleasure to be here to talk about hydrology and machine learning. How many of you here are hydrologists or groundwater hydrologists? Okay, at least a third. So nice. We were often the majority. Now we take a minority role. Okay, so a lot of this work is done by my student, Chaopeng Shen here, and Dr. Kuai Fan here, who has moved on to Stanford University. And you can download our code here on GitHub. And before I dive in, if you follow me on Twitter, I'm posting a lot of useful information every day, so please do that. So I've been promoting the role of deep learning in hydrology for some time through these collective opinion papers, review papers, and editorial articles. Today I want to talk about how hydrologic deep learning has evolved from a niche tool to offering a full suite of services. And then I'm going to give some literature review and outlook on groundwater and subsurface modeling. You know, on this topic, the light of big data hasn't shined below the surface. Of course, it's a different situation what our previous presenter has provided. But I'd say, even that is the case, that does not mean that deep learning is not applicable to this situation. Okay, so what do hydrologists do besides entertaining ourselves? We want to show responses of hydrologic variables to external perturbations. We want to show long-term projections. I guess this would also work. We want to quantify the uncertainty, that is, we want to put error bands on the predictions that we make. We want to make forecasts, update the states in the variable. That is, when you have predictions, you won't have all the information you have today, you want to predict tomorrow. We want to predict in ungauged areas, in places where we don't even have data. We want to predict unobserved variables. So these all pose challenges for machine learning. A lot of times we build a model between X and Y, not to just make a prediction, but also to understand what is the relationship between X and Y. Okay, so my case studies, I'm going to talk about the SMAP soil moisture active passive satellite. It was launched in 2015. It has a revisit time of 2 to 3 days. It senses the top surface soil moisture around the world at its regular revisit time. And the second is streamflow data from the KMOS dataset. It has 670 basins around continental United States, and for each basin you have a set of time series as well as static attributes. And the third one is not a case study, but more literature review and outlook, that is the subsurface flow and reactive transport modeling with machine learning and limited data. So LSTM, the long short-term memory model, is the one that we're using for some time. It was normally used for natural language processing tasks, for example, machine translation or speech recognition. All the things that wake up when you say, hey, hello Google, they wakes up. So in our setup, we feed atmospheric forcings and optionally land surface model outputs, and then a bunch of statistic attributes into the LSTM model and have it predict an outcome which is matched with the observations, right? So this was never meant to be. There was never meant to be a dynamical model, but we used it and it gives us great results. The first paper we published in 2017 is about modeling the SMAP data. So essentially, we trained the model in 1 year using SMAP data and the forcing data, and then we tested it in a different year. As you can see, some of the pictures are highly successful. It's almost the blue line, which is the LSTM, it's almost following the observation, which is the red circle, almost exactly. And we tested over continental United States. Every pixel is a separate instance. So we get an R of 0.9 across the vast majority of continental United States. It doesn't really work in this northeastern area because of heavy vegetation content. That's a limitation of the SMAP data itself. If it works very well there, I'd be really concerned. And we compared it with different statistical models, autoregressive models, as well as the null land surface model. And the LSTM has the highest anomaly correlation with the observation and also the smallest bias. So we were questioning ourselves, does this work when you have a mild non-stationarity, which is a question that is often thrown to us. So I checked ourselves. We trained the model in 3 years, and we tested in another 3 years. And we check if the model can capture that multi-year trend. So the x-axis here was the trend measured by in situ data, whereas the y-axis is the trend in the testing period from the LSTM. So it seems, given mild non-stationarity, the model can predict that multi-year trend. But we haven't tested it for strong non-stationarity cases. So this was published in 2018. Of course, coming to the third topic, that's uncertainty quantification. I'm very pleased to hear that our previous speaker has talked about doing UQ using Monte Carlo dropout method, which is also the method we used. But we also look at having a term, having a neural network term to predict some of the parameters in your error model. So basically, you're asking the neural network to build an error model for you. So instead of assuming Gaussian model, assuming various different variances, you actually have the model to build that model for you. So this is a huge advance. If you're doing uncertainty quantification, you really need to wake up here. Okay, we actually got a correlation of 0.84 between our estimated uncertainty and our predictive error in the prediction in the test period. Okay, so we're really moving forward. We're trying to get at how do we estimate the states and fluxes that aren't observed. So we come up with this new parameter inversion network where we actually build a new network. We give the model the forcings and the responses, and we let this model infer parameters for the weak hydrologic model. So this is a very widely used hydrologic model, and you need parameter calibration. It's a pain in the neck to do calibration for these things. But now we built this network to do it, and we have it to predict the y, which is then compared with the observations. And this is some of the results, and we're writing this paper up. It has got very good results over continental United States comparing with the SMAP data. Actually, it's stronger than the standard shuffle complex evolutionary algorithm. Our correlation is actually higher than the site-by-site or pixel-by-pixel calibrated SCUA. So this is such a huge advance, and very excited about this. I think it's certainly going to change the field. If you're running these calculations over a kind of scale, normally what you do is you put it through 100 processors, run it a couple of days. That's what's typically involved. Now we need 1 GPU and 15 minutes. So if you calculate it, it's 5 orders of magnitude savings in computational time, or 3 orders of magnitude savings in actual clock time. And we're actually stronger. So this calibrated model now allows us to predict variables that are not observed, such as evapotranspiration, or sometimes streamflow when you don't have observations of this. Now the fourth topic is about forecast. When you're doing forecast, you have all the information, all the observations until yesterday, and you want to use them to predict tomorrow, right? All you care about is how good you can do for tomorrow. And so we proposed a neural network formula that integrates the information from yesterday and predict tomorrow. And we also dealt with a situation where you actually have some gaps in that observation data, because this data is actually irregular. So with those data integration, what we call data integration kernels, we're able to improve the prediction R from 0.85 to 0.92. And we compared it with literature models, which you see this is the error. You have lots of error with the literature model, which is like a piecewise linear regression model. And our model almost has very little errors there. We achieved like 30% reduction in the error. And this was published in 2020. We applied the same formula for streamflow prediction. And this time, we sent the lagged information into LSTM or through a kernel, through a CNN kernel, CNN STM. In the end, directly feeding LSTM works very well. We apply this to the KMO streamflow dataset, and over the continental United States, we were able to push the median NSE, Nash Sutcliffe coefficient, to 0.86. So that's ridiculously high. It's most unheard of. So the previous record was 0.73, something like that. So this paper should come out soon. So now the next question is, how do you make predictions when you don't have such detailed data? For example, many catchments in the world, and in China, in India, don't have such detailed daily data, but they can offer you statistics such as the flow duration curve. So we actually trained a model that sends the flow duration curve into the CNN LSTM and use it to make predictions. It allows us to make predictions where the attributes aren't really there, and give us a prediction accuracy that's similar to when the attributes are there. Okay, so I use this figure a lot. It's talking about the relative strength and weaknesses of process-based neural network models. The process-based models, it's built from the bottom up, and I hope it's a strength that we know what we put in. It's sometimes not the case, but anyway, there's huge human biases with the process-based models because when someone did the analysis, the number one criteria for you to select a hydrologic model was which group you're educated in. All right? But now actually I want to focus on the limitations of big data and machine learning. It can't observe everything, so that alone precludes you from building machine learning models everywhere. It can be difficult to interpret. It does not respect physical laws, which bothers us a lot, and it does not understand causal relationships. So that's more so the case for groundwater. Okay. I have an upcoming review article, book section about, there have already been many studies that look at individual wells and predicting well levels using LSTM. So I'm not going to spend too much time on that. But what is actually more interesting is the parameter inversion, similar to what our previous speaker has discussed. So our thought has always been that we have some numerical models that go from a parameter fields, for example, K, to states, for example, groundwater head. But for neural networks, it's the same thing. You can go from K to the head, but you can also go from the head to the K. And for it doesn't make a difference, right? So that inversion process now becomes a forward process. And this was published in 2018 by Alexander Sun, that he shows that we were able to retrieve that conductivity field relatively effortlessly using a neural network. So more recent research by the Zabras group, they look at turning the numerical simulations into an image-to-image regression problem. They can actually do such training without training data. What actually happens, they build the partial differential equation into the PDE that reduces a lot of the intricacies and delicacies of providing training data. Of course, that inversion isn't unique, so you can use GANs to generate. You can use the generated adversarial networks to generate a range of scenarios instead of giving one optimal fit to a problem. So we've recently been working with, this is more an outlook than established results. Been working with physically informed neural networks. This is in the spirit very similar to what Vipin has talked about it last time, but it is also a little different in the sense that PIN really just uses neural networks to solve PDEs. Okay, so once you have this neural network which solves, for example, divergence law, you can then use observations to further improve that. Okay, so if you compare it with the pure neural network solution, it really reduces the data demand. It gives you seamless and interpretable 2D or 3D outputs. It output unobserved variables. If you compare it to a numerical solver, it's much, much faster. And there are fewer numerical stability issues. It's trainable. Once you have the PDE working, you can further improve it. This is what you cannot get or having a hard time get with the numerical solutions. You can further improve it in more data. You can, as we have shown, you can actually condition this model to ask a different question. Instead of asking it, okay, what's my results? You can ask it, oh, what's my parameters? Or even you can ask it, oh, what is my constitutive relationship? Or causal relationship. So this really is a change of the way of questioning, right? A change and greatly liberated us from a lot of the traditional norms. So where do we go from here? I think that the hydrologic deep learning will launch a full-on assault to offer a full suite of hydrologic services with higher accuracy and lower cost. Deep learning will not replace process-based models. There will be a class of unified models that links together process-based models and deep learning. So when I write this, anecdotally, when I wrote this initially in my first batch of proposals, I actually wanted to put them in to appease our fellow reviewers, and they saw me through and killed the proposal anyway. That was supposed to be a joke. But actually, after thinking about it more and more, I believe in this more and more, that we absolutely will have this merge between the two. The powerful applications have already emerged in hydrologic deep learning. While the PIN has nearly completed its proof of concept, so there's more opportunities there. In the future, a PIN might see more growth. Deep learning may be deeply ingrained into next generation models for science and practical operations. I wrote an editorial article in 2018 where I said, perhaps one day deep learning will become an inalienable component of the hydrologic discipline itself. And here I'm going to leave up my review articles and a shameless plug for another project of mine, which is funded by Google to look at the landslides from a big data perspective. And I leave up some links and questions. Am I running too fast?
Thank you, Chaopeng Shen, for this great insight. Yeah. Are there any questions? Okay, no questions for now. Yes.
Yes, yeah. My question is, it's Erik Larsen again, Earth Science Analytics. How do you envisage that we will, in various disciplines, integrate the physics-based models with deep learning?
Yes, I think we have a lot of good experiences from Weiping yesterday, but from my perspective, what I can add is I think the PIN method, by actually putting the spatially distributed partial differential equation into the network, that will grow. They can actually train the model without preparing training data. So that will remove a lot of the trouble for preparing training data sets. There's a range of other techniques from what Weiping talked about yesterday, including pre-training to adding regression law, to adding physical constraint into the loss term, and many other methods in the review papers. But we are working on the PIN thing. Yeah.
Thank you. Another question? No. Yeah.
Maybe at the risk of getting into your coffee break. No, a quick question is, thank you very much. Hydrology and geology for petroleum resources have quite a number of things in common, because we need to look at the dynamic fluid flow, basically. How much have you compared the methods in both disciplines to learn from each other?
That's a great question. I have not compared between hydrology and hydrogeology per se. I think the Darcy's law are pretty similar, but actually in my review paper I have compared methods from physics, computational biogeology, and chemistry. And I believe there's a lot to learn across the boundaries. In fact, when I put those content there, the reviewer was saying, "Why do you put this content here? It's not relevant to us." But I was saying, this is the treasure, because if you look at around the different disciplines, the physics, chemistry, biology, they are moving so fast. They've already developed so much, and they're using these techniques very creatively. Whereas in hydrology, we're moving slow. I don't know for what reason, but there's a lot to learn from what the other disciplines have done. And I think that there will be some things that is going to evolve from hydrology that's unique to offer to the scientific. Yeah.
I may invite you in the poster session, the breaks, because in petroleum geology we have found ways to combine physics-based models with deep learning to predict better outcomes, if you like, of volumes being produced, or injected. So very, very similar to hydrogeology. Would like to have that discussion with you.
Absolutely, yeah. Seems something like the pins thing, or very nice. Very nice.
Okay, thank you so much.